Welcome to qnawire.
Our question wants us to consider two Helmholtz coils where you can look at figure 58 to get a diagram of their layout. So for part A, we're asked to determine the magnetic field at B, at point X along the line, joining the centers. So X equals 0 is the center of one coil, and X equals R is the center of the other coil. And I have some values written for R, number of turns, and the current I. We're going to use those for part C of this question. So for part A, we're going to let point P in the diagram lie at a distance x from the left of the coil to the right. So the magnetic field at that point from the left coil we'll call B1, where B1 is equal to, the equation is number of turns times the magnetic permeability of free space, mu naught, times I, times R squared, divided by, we have 2 times x squared plus r squared. And then this all gets raised to the 3/2. And this is in, let me write that too. This is in the I hat direction. And B2 is very similar. It's equal to, again, n mu naught times I times r squared divided by 2. This time the first term isn't x squared, it's x minus r squared. Plus r squared. And again, this is all raised to the 3/2. And all in the I hat direction. So then the total magnetic field at that point, this is what we're asked to find for part A, we can define as B, and it's simply equal to B1 plus B2. So n, mu naught, I, r squared, and the 2 are all the same in both, so we can pull those out front. So we have n mu naught times I, r squared over 2. And then in the brackets, we can put everything else. So the first one we have 1 divided by x squared plus r squared to the 3/2. Plus, and then the second one is 1 over x minus r squared plus r squared to the 3/2. Let's rewrite that. And both of these are acting in the I hat direction. So on the outside of the bracket, we can put I hat. And that can be boxed in as our solution for part A. Part B wants us to show that the field midway between the coils is uniform by showing that the derivative of B with respect to X is equal to 0 and the derivative squared of B with respect to X is equal to 0 at the midpoint. Well, at the midpoint, X is equal to R over 2, right? So for both of these, we're going to consider when X is equal to R over 2. Okay, so the first one, dB dx. And also for simplicity, I'm going to make a little substitution here. So I'm going to say that the constant C is equal to the number of turns N times mu naught times I times R squared divided by 2. And the reason I did that, if you go back here, you have that out front, n mu naught I r squared over 2. Just so I don't have to write that over and over and over again, because that doesn't have an x dependence. We'll just write that as the constant C out front. Okay, so now I'm just going to take the derivative of the rest of B with respect to x. There's a, you end up with this negative 3/2 from both terms. The reason is because you go back here, you have each if you look in the bracket, each of the denominators is raised to the 3 halves. So that's to the negative 3 halves since they're in the denominator. So you take the derivative of that, that comes out front using the product rule, right? And then you're left with, so now we're going to do the first term. We have 2x because you have x squared in there. And then now this is x squared plus r squared. And it was originally raised to the negative 3 halves, but negative 3 halves minus 1 is negative 5 halves. So now it is raised to the 5 halves. And then the second term, the x was r minus x squared. So you have a 2 that comes from the r minus x squared. So the squared term comes down front and gives you a 2. Then you still have r minus x. Then you have to take the derivative of what's inside, which is minus x. The derivative of minus x is negative 1. So you have to multiply this by negative 1. And then this gets divided by, you still have r minus x squared plus r squared. And this all gets raised to the 5 halves. All right, and I think I might have had a typo if we go back. Yeah, I wrote x minus r squared right here, as well as above, and this should be r minus x. So let me fix that real quick. Apologize about that. You might have been wondering if you're looking at the diagram, it's pretty obvious it should be r minus x because the total distance here for that one is r, and we're considering a distance that's closer to the first coil than the second coil, so it should be r minus x. Okay? So now we just simply plug in x equals r over 2 into these. And what do we get? So we still have c times negative 3 over 2. So we're just going to call all of that c. So we're going to let that negative 3 halves get consumed into the constant c. Because what we want to show is this is equal to 0. So clearly c times negative 3 halves isn't equal to 0. So whatever must be in the bracket must be equal to 0 when we plug in r over 2. So 2 times x, which is r over 2, gives you r, divided by, you have r over 2 squared plus r squared. And this all gets raised to the 5 halves. Plus, now you're going to plug in r over 2 for x again. So you have 2 times r minus r over 2 times negative 1. That gives you negative r. Divided by, and then again, x minus r minus x squared, where x is r over 2, gives you r over 2 squared. So you have r over 2 squared plus r squared. And this all gets raised to the 5 halves. So there it is. That shows that it's 0 because what we have here in the brackets, let me fix this left bracket to, there you go. What we have in the brackets is one value minus the exact same value because you have a negative r on the rightmost term there. So this comes out to equal c times 0, or in other words, this comes out to equal 0. So that's the first part of what we were asked to prove. Next, we need to take the derivative of this again and then plug r over 2 in again to show that this is also 0. So if we do d squared of b by dx squared, now we just need to take the derivative again of what we found, and I'll underline it in red. Essentially, we're taking the derivative of what I just underlined here. So that term there. Okay. So we still have that constant c, right? And now we're going to take the derivative of what's inside the brackets for the previous x. So this is, the first term gives us a negative 5 halves because we were raised to the negative 5 halves there. Then this is 2x squared now. It's the same thing as before. You end up with that 2x on top, but we already had a 2x on top, so that 2x is now squared, divided by x squared plus r squared. And we were raised to the 5 halves, but 5 halves minus, or negative 5 halves, 5 halves minus 1 gives us negative 7 halves. So we have 7 halves on the bottom. Plus, now we need to take the derivative of what was on top, and it was 2x. So that just becomes 2 divided by x x squared plus r squared to the 5/2. So that was all from the first term using the chain rule and the product rule. The second term, now we have plus. Before we had a negative value here. So this is going to be plus, you have 5/2 times 2 squared times r minus x squared. And then you also had -1, but that gets squared, which is just 1. And then this is divided by, you have r minus x squared plus r squared to the 7/2. And then you have to add one last term. We're in a room there, so I'll just write it below. You have plus, or excuse me, it'll be minus this time because remember it was negative. So you have minus 2 divided by r minus x squared plus r squared, all raised to the 5/2. Okay, so if you'll notice here, again, you have two terms in the brackets that look like they match. So you have this term here is equal and opposite almost from this term here. They're close, but you have an x squared and one of them has an r minus x squared. And then this term here is almost equal and opposite to this term here. Again, you just have an r minus x and an x squared. But when we plug in x is equal to r over 2, these terms become exactly equivalent. So just as before, you end up with c times 0 in the bracket when you let x equal r over 2. This is only true for x equals r over 2. If you plug in any other values, those terms don't cancel. This ends up being c times 0, which is just equal to 0. And we can box that in as our solution. Now for part C, the final part here, we're asked to show that if r is equal to 10 centimeters, n is equal to 250, and I is equal to 2.8, what is the value at that midpoint x equals r over 2? So what we can do then is if we go back here, these are the values written up top that we have. I converted centimeters into meters. So what we can do is we can just simply plug in to our original expression that we found here that's boxed, what we have boxed in here. We can just go ahead and plug our values in to this expression, but replace x with r over 2. So what do we have here? We have b is equal to, and I'm going to replace the constant back with the actual values because we're going to do a calculation. So this is mu naught times the number of turns times I times r squared all over 2. And then this gets multiplied by, we have 1 divided by x squared plus r squared, where x squared is r over 2. So this is r squared over 4 plus r squared. This all gets raised to the 3/2. Plus 1 over r minus x squared, which is r over 2 minus r. So you have r over 2 squared plus r squared, all raised to the 3/2. So if we plug in our values that we were given, and mu naught is 4 pi times 10 to the minus 7. If you want to look up more about that constant, you can. And this comes out to equal 4.5 times 10 to the minus 3 Tesla, or 4.5 millitesla. And we can box that in as our solution for C in the final part of our question.